Archimedes principle. So the first thing we'll look at is the displacement rule. So a completely submerged object always displaces a volume of liquid equal to its own volume. So we can see in the figure below, if you place a stone in a container that is filled to the brim with water, and the amount of water overflows equal is always equal to the volume. So you can even try to do this experiment at home, and you see that it's easy. This is one of the easiest way you can do to measure the volume of any irregular object. So if we look at the first example, so an object is completely immersed in a liquid. Now, what we are saying is from this example, if you take a 3 kilogram mass of an object and you weigh that in air, and if you also weigh that in water, you'll see that there will be a difference in the weight that you get. And so the difference that we get is as a result of what we call the buoyant force. So you see, for the first case, you see that when the object is in air, the mass of the object is 3 kilograms, and the other figure just in the right talks about is zero. So at that point, the weight of whatever pan or whatever dish we're trying to measure is zero grams. Now in air, the mass of the stone is 3 kilograms. Now we see that now when we submerge that into water and we take the measurement, you see the measurement is just 1 kilograms, but now the measurement of the displaced liquid is 2 kilograms. Now because so if we find the difference between when the object was in air, the mass of the object in air versus the mass of the object when it's in water, you see that in air the mass was 3 kilograms, in water the mass was just 1 kilogram. Now if we look at that difference between those two masses, it gives us 2 kilograms. So the buoyant force therefore becomes the difference between those two forces. Now, because we have the difference in forces in masses, which is 2 kilograms, we can therefore calculate the buoyant force. So the buoyant force will just be 2 kilograms um, times 10, which is acceleration due to gravity, because we talked last time in class that the weight, which is a force, is equal to the mass times the acceleration due to gravity. In this case, we have the mass to be 2 kilograms, and we have the g to be 10. So it's possible for us to calculate the buoyant force from this particular method. Now, what about a case where an object is just partially immersed in a fluid? So we consider a case, you see, now in the first case, you see that an object is totally immersed. In this case, now we see that an object is partially immersed, and you can see the buoyant force. What the buoyant force does is it tries to push the object upward. And we can see those two arrows, buoyant force, you have the um, the pink arrow going upward indicating the buoyant force, and the weight of the iron going downward. You see that there is a balance in those two forces. Now the weight of the object balances the buoyant force. As a result, the object has to float. But if you look at the first case on the far left, the buoyant force is smaller than the weight of the object, and as a result of that, the object has to sink. So generally, when we want to in submarines or building in ships or whatever, we have to take into account the weight of the ship and the force, the buoyant force that will be exerted from the bottom of the ship upward. Now if that difference is zero, then we expect the ship to float. But if the difference is not zero, if the buoyant force is less than the weight of the object, then obviously what will happen is that object is going to sink. And that's kind of like a principle that we're trying. That's why the Archimedes principle is very, 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 very important when we are talking about applications in aerodynamics, in a normal day life. It's a very important principle. Now let's look at pressure in gases. We already talked about pressure in liquids, and which say that in liquids it increases with depth. The higher you go upward, the lower the pressure. The higher you go down, the lower you go downward, the higher the pressure. And we looked at that concept. So now let's look at pressure in a gas. Now, the gas pressure is the amount of force per unit area that a gas exerts against the containing wall. So if I put a gas atom, if I maybe nitrogen or hydrogen or whatever the gas may be, if I can be able to collect hydrogen gas into a certain container, and I want to measure the pressure, the gas pressure, it will simply be the amount of force that gas molecules inside that container is exerting on the walls of the container. And here, the force is exerted by the motion of the particles bouncing around. So we explained that the force of attraction for gases is very, very small. Yeah, it's very, very small. The separation distance is very, very wide. As a result, the molecules can bounce around each other. They can vibrate. They can oscillate. They can move in various directions randomly and hitting each other. And therefore it's possible for us to measure the force at which they are hitting each other and they hitting the walls of the container. And since we know the area of that container, it's possible for us to determine what the pressure of the gas will be. So, for example, if you look at the case we have here, in this case, we have a container and we have a certain amount of molecules in that particular container. But now, if we double the molecules, if we have twice as many molecules in the same volume, then what we are saying is that the pressure will double because we have double the amount of molecules, and we're also saying that the density also is going to double because we have as much twice as much molecules as the previous one. So what we're indirectly trying to say is that if you double the density of the air, what is going to happen is that in order to do that, we have to double the amount of air, which we've explained in the previous slide, and we have to decrease the volume to half. If you decrease the volume to half and you still have the same amount of air, then the density is going to double. And we say that, so if you double the amount of air in a container and you decrease the volume by half, what you're doing generally is that the density will increase, and also the pressure will also increase. So you can look at it for the first case. You see some certain molecules, and you see a pointer that tries to measure the pressure, and you see that if you reduce the volume, you see that the pressure increases too. You can actually see